when measuring the wavelength of radiation. What's actually being measured? So, I have two competing mental models of what is from a mechanical perspective. Turns out a mechanical perspective might not be possible, which is distressing. 1. Photons are not radiation, but they have fields around them in the same way that, say, protons and neutrons have fields that interact with each other. And those fields are where the waves come in. These fields are not governed by particles, but are rather some other star. Or 2. Star radiation, and they move in a straight line. But only when we're paying close attention, because wave-particle duality. They are the medium propagating the waves. I must be wrong either way. Because we star these waves in terms of length, specifically in nanometers. I'm inclined to think that I'm closer to reality with number 1, considering that reducing all forces to collision is apparently a lost cause. https://m.wikipedia.org/wiki/action at a distance which my brain is really having trouble accepting as anything but magical thinking. If number 1 is closer to the correct way of viewing things, you're telling me that this particular spooky action at a distance occurs over great enough distances to be expressed in nanometers? And more importantly, how can we even measure that it occurs in waves spanning nanometers? I know it's describing a vector field, but doesn't that still require that could be detected and measured as having a velocity, and therefore momentum and mass, i.e., a bunch of particles? And what do photons in this context? I've seen them described as essentially a side effect. I love all the discussion occurring, but it's also made me realize that the body of my post mostly goes beyond the question. The question being, we're able to describe the physical wavelength in nanometers of these waves that apparently aren't oscillating in space so much as they oscillate between electric and magnetic fields. How do you assign a unit of length to that? The answer: I'm an grad student who's specializing in microwaves and antenna theory. So a good way to think about this is that changes in the electric and magnetic fields don't propagate instantly. They travel at the speed of light. So if I turn on an electromagnet, it will take some time for any metal near it to feel that force. Even though that time will probably be measured in nanoseconds, it still takes a non-zero time between the magnet being energized and for the metal to feel the magnetic force. Now imagine an antenna as a tiny electromagnet that's being flipped from positive to negative billions of times a second in a sinusoidal pattern. This is oversimplification of what an antenna is. But for the purposes of this discussion, it's enough. The changes in the field will only propagate at the speed of light. But the magnet is changing extremely fast. This makes it so that if you take a snapshot of the magnetic field at a single instant, you will see the field shift from positive to negative with distance from the antenna. If you measure the distance it takes to go from positive to positive again, that's your wavelength. Here's a GIF of an SYS simulation I made of the electric field of a simple dipole antenna over time. https://jiffy.com/gifs/36i4oh9p4art. You can see the wave-like pattern in the field magnitude. And here's one I made of a Yagi antenna. https://jiffy.com/gifs/mesbeeb3sv7 Follow this channel for more Santa Explains.